We're continuing the same question from part 1 and 2 of the application of Bayes' theorem. Mary is being tested for a rare disease. 1.5% of the population has the disease. So P of D is 0.015, P of ND is 0.985. First, a group of people who have the disease are tested, 99% test positive. So probability of positive, and we know that this group has the disease, so probability of positive given disease is equal to 0.99. The opposite is 0.01, which is 1 minus 0.99. Next, a group of people who did not have the disease were tested, which means that we know they do not have the disease. 2% tested positive. So probability of positive given no disease is 0.02. The opposite is probability of negative. We still know they don't have the disease, which is 1 minus 0.02, which is equal to 0.08. In part 2, we found the probability that a randomly selected person shows positive. And we said that we don't have the probability of positive in these 6 listed probabilities. So we have to do a little bit of work. So we said that we could think of 2 cases. Someone could have the disease and show positive, or, so the important word here is or, someone does not have the disease and show positive. For the or, we use the addition rule. And so we break this down into probability of D and positive plus probability of ND and positive. We break it down further. For the word and, we use the multiplication rule, and here we have dependent events because showing positive does depend on the probability of showing positive obviously depends on whether we have the disease or not. So they are dependent events. So we use the multiplication rule for dependent events. So that is probability of D times probability of positive. But then given that D, the person has the disease, plus we do the same thing. The and gets converted to times probability of ND times probability of positive, given that the person has no disease. We plug in the numbers and we got 3.5% approximately, but the number was 0.03455. Now, we're going to find the probability. Let's just say Mary tests positive. Okay, so we know that she tests positive. Okay. What is the probability that Mary has the disease given that her test shows positive? So if the test shows positive, it is not necessarily true that the person has the disease, because sometimes there are false positives. So if someone gets a positive test result, what is the probability that they actually have the disease? So it would be probability of disease given positive. So this is a conditional probability. So if you remember from before, probability of D given positive is probability of both in the numerator, because it's a quotient, divided by probability of positive in the denominator. So that's the rule. It comes from the multiplication rule of events that are not independent. So now probability of both is probability of disease and positive divided by probability of positive. Now probability of disease and positive, we've already calculated that. It's the probability of disease times, so the word and goes with the multiplication rule. Since the events are not independent, we use the multiplication rule for events that are not independent. So it's probability of the first event, which is disease, probability of the second event, but since there's dependency, we go given that, knowing that D happened, divided by probability of positive. Remember that we've already figured this out. Probability of positive has already been figured out, and that is equal to 0.01 0.03455. Plug in the numbers in the decimal form. Probability of disease, we look at this original list of 6 probabilities, which is 0.015 times probability of positive given disease is 0.99. So this is equal to So it is 0.4298 when we use our calculators to make those calculations, to do those calculations. And approximately that would be about 43%. Okay, we first convert it to a percentage, which means we shift 2 decimal places to the right. So that's 42.98, which is approximately 43%. So if a random person goes in for the test and they test positive, the probability that they actually have the disease is not 100%. It is only, in this case, 43%. So there's a good chance that the person does not have the disease, even though they've tested positive.